Mechanical analysis of a left crank arm of a road cycling bicycle. Group 14.
Introduction. This research presents stress analysis for the left crank arm of a bicycle. The crank arm undergoes typical loading of 540 newtons and worst case loading 1690 newtons at 90 degrees. It features a solid circular cross section. The combined stress states acting on the bicycle crank were also analyzed. Thereafter, a new shape and cross section of the bicycle crank is suggested. Assumption. Stress analyses are limited to circular cross sections. The holes in a bicycle crank do not create a stress concentration. Forces from the worst case scenario are used to analyze stresses. The mass of the crank arm is negligible compared to that of the forces applied on the pedal. The rider's pedaling technique has no contribution to the applied forces on the pedal. Forces applied on the pedal act downwards. The friction between the pedal and the crank arm connection is neglected. Target user is a professional cyclist of 68.8 kgs and 1.8 meters height. Dimensions of the crank. The crank arm is precisely calibrated to the rider's height, and the chosen dimensions are crank length 175 millimeters, crank diameter 25 millimeters, crank thickness 4.5 millimeters.
Free body diagrams and force analysis. There are two figures on the left-hand side of the screen. Figure 1A showing a 3D drawing of the left crank arm, showing section lines AA at the critical point. This is relevant for later stress calculations. And figure 1B, a free body diagram of the crank arm, showing reaction forces and moments. There are four main quantities in this free body diagram, the first being Fp, which is the force on the pedal. This is the force that is applied by the rider's foot, which acts vertically downwards. It creates a torque and bending moment on the crank arm. Secondly, the reactions on the bracket. This is where the crank is attached to the bike frame. Rx and Rz, which act along the x and z axes respectively, inducing shear and bending stress. This balances the system, ensuring static equilibrium. Torque, indicated by T, represented along the x-axis, indicating a rotational force and creates a maximum torsional shear stress at the outer surface. And lastly, bending moment, MB, applied along the y-axis and produces tensile and compressive stresses, peaking at the outermost fibers. On the right-hand side, you can see a force versus angle graph for the typical and worst case loadings.
Stress analysis and formulas. In this project, the analyzed stresses were bending stress, normal stress, torsional stress, and transverse shear stress. Known formulas as listed below each stress subheading were taken from the Mechanics of Materials textbook by R.C. Hibela. The formulas were further developed by substituting known constants such as the radius, the perpendicular distance from the neutral axis, and further simplification was also done for the stress formulas to eliminate complex variables such as the area moment of inertia, polar moment of inertia, shear force, and area, such that each formula was broken down into a simplified version which only contained the known variables, such as the force on the pedal and the bending moment and the angle theta.
The graphs below analyze the individual and the combined stresses acting on the bicycle crank arm for the worst case loading. Figure 3.8 displays the effect of each stress individually acting on the crank arm. It can be seen that the bending stress has the largest quantity at the critical points of the revolutionary motion, specifically at 90 and 270 degrees. The axial and transverse stress are relatively small and may be considered negligible for future applications. It can also be seen that the torsional stress is always positive for the overall motion, indicating twisting in one direction. Figure 3b displays the magnitude of the combined stresses, namely the normal and shear combined stress. According to the graph, the normal stresses contribute the most at the critical points. The table below is a summary of the exact values displayed on the graphs at key angles.
Critical combined stress. From figure 3b, the combined normal stress is the highest peaking graph at 90 degrees, making it the critical stress. It results from a large moment induced by forces applied on the pedal during cycling, with the highest stresses near the connection to the bottom bracket. The combined critical stresses act at the root of the crank arm near the bottom bracket and the spindle connection, where the bending moment is maximum. From figure 1, a cross section about AA is analyzed below at 90 degrees. Figure 4a shows the combined normal stress distribution at this cross section, and 4b shows the combined shear stress diagram. From figure 5a, 2 points A and B were taken along the circumference of the cross section, and stress elements were drawn at each of the points as shown below in figure 5b.
Suggested shape and cross section. The current design of the crank arm is a solid cylindrical shaft with a diameter of 25 millimeters. The proposed design is a hollow cylindrical shaft with an outer diameter of 30 millimeters and an inner diameter of 20 millimeters. The proposed design has a greater moment of inertia with the specified dimensions, which in turn provides the crank arm with a greater resistance to the bending stress. The cross-sectional area of the crank is also reduced, thus reducing its overall weight. This configuration optimizes the strength of the material whilst reducing the cost of manufacture, thus satisfying the requirement of the engineer.
Table 2 shows the properties of the materials used to manufacture the crank arm. The materials which were considered are aluminum, steel, and titanium. Under the analysis of the materials, aluminum has the lowest E value, indicating that it deflects most under the same law. To prevent this deflection, its moment of inertia needs to be increased by having a larger outer radius and a smaller inner radius, thus increasing the thickness of the wall. Steel has the largest E value, indicating better resistance to bending. The cross-sectional area of steel does not significantly have to change. Titanium has a value for E greater than aluminum but less than steel. Decreasing the inner radius of the crank arm will increase the overall thickness of the titanium crank. This will increase the moment of inertia of the crank arm. For contextualization, aluminum is perfect for lightweight application as it has a low density of 2,700 kilograms per meter cube. It is also more affordable than titanium and steel. Steel has higher strength and stiffness of 500 MPa and 205 GPa respectively. However, it has a higher density which results in the increased overall weight, making it more appropriate for applications where durability outweighs the need for weight reduction. Titanium combines high strength of 880 MPa and a relatively low density of 4,430 kilograms per meter cube, enabling the smallest and the lightest cross-section of the three. Conclusion. Aluminium requires an increase in the moment of inertia, steel requires small or no change in the moment of inertia, and titanium also requires an increase in the moment of inertia.